Hi everyone. Today I would like to go over data structures and algorithms. And the survey I had sent out in for phase three in order to figure out how to best prepare everyone for doing interviews, technical interviews. I did ask a question where I listed a bunch of things that were kind of computer science like topics, things that you probably, if you had a CS degree, you would have heard about all through your coursework there. But Reskill Americans isn't really doing a computer science course per se. We are more kind of practically oriented and enabling you to actually build websites, build applications, but haven't focused very much yet on things like data structures and algorithms. So that's one of the things we want to do today. So I put together a kind of a crash course in data structures and algorithms. The point being, this is not enough time to really understand all of these topics in depth. But if you're in an interview and someone asks you about automatic garbage collection or linked lists or binary trees, you should be able to know what they're talking about and be able to at least have some kind of a discussion about why you would use those or when those would come into play. So let's go ahead and get started. So what are data structures and algorithms all about? It's really not anything that hard to comprehend. It's really how do you represent things on a computer and then write code that will manipulate those things or be able to read and write those things to actually perform a task. And to do so in a way that actually performs efficiently is usually a concern, and some algorithms are better than others. So let's just talk about that. Just get started. But I think one thing that really is a good prerequisite for talking about any sort of data structures and algorithms is to understand really the memory structures in a computer and how those relate to when we write code in a high level language like JavaScript or Python. I think in the back of your mind you should be able to know like a little bit about what's going on underneath the covers in the computer and how it affects things like the performance or the reliability of your program. So let's take a look at some things. So one thing is just the memory, the RAM in the computer. You say you have 4 GB of RAM or whatever it is on your computer, and if you run a program, some portion of that memory gets allocated to your program, and that could be a web server, it could be the browser, and it is going to allocate some memory according to that. And so you typically would think of like all of memory as this big block. And when you create when you allocate data structures out of this big block, you might get various regions of this memory allocated to your program. So this could be like a variable. If I say x equals 5, that variable might sit in here, and maybe this is only taking up 4 bytes of storage. So these would be bytes in an array of memory on your computer, and it gets interpreted in different ways. So some of them are going to be variables, others will be structures. So if I have an object, a JavaScript object where I have a name property, and then I have an age. This object written in JavaScript actually gets stored in some sort of data structure that takes up some bytes of memory. And so there'll be a field for the strings and another for the number, and the computer has to basically allocate all of this stuff out of RAM and know where to store it and then where to retrieve it. So every piece of memory has an address. So like the things down here might have an address of 0, and things up at the top might have 1 billion. They might have a really high address. So there's an address to this position in memory, and then a certain number of bytes that represents this data structure. So all data structures are made out of this kind of thing, where you have a memory in the computer, and the programming language you're using is allocating things out of this heap, what's called a heap in the data structure. So what happens when we're writing a program and we say something like x equals hello and y equals 100? These things have to get allocated in memory, and in most of the programming languages we're dealing with in our course, they are being dynamically allocated. So that means that at the time that your program is running, the computer sees where is there some available space in that heap of memory that I have, and it will just allocate this. So if x is supposed to say hello, so I am going to need 1, 2, 3, 4, 5, probably 6 bytes of data here, and it'll just have the letters in one letter in each byte, for example. And so it'll allocate that memory when that first line is executed. And then when I say y equals 10, maybe it'll put that value in the very next 4 bytes of memory. So numbers have a given size, and strings are usually either 1 byte per character, or sometimes they're multiple bytes per character. So in the browser, for example, most numbers take up 8 bytes of memory. They use an IEEE floating point number format, which is kind of complicated to explain, but just know that any number is going to take up 8 bytes of memory. So in JavaScript or other dynamically allocated programming languages, you're going to have something called garbage collection. And garbage collection allows you to reuse memory that you no longer need. So if, say for example, here I were to say x equals 7, after saying x equals hello up above, then this memory is no longer needed, and I'm going to have another piece of memory that's going to hold this new value. And so x is going to point to that, y points to this, and there's a bunch of unused memory here that I no longer need. So the memory manager inside of Chrome is actually going to go through and handle whether how that memory gets reclaimed. So usually what happens is after any piece of memory is no longer referenced by any other variable in your program, it's kind of what's called an unreachable block of memory. So this can get reused, and then in the future this would then be freed up so that some other thing could use that same piece of memory. So this all falls under the term automatic garbage collection. So in garbage collection, there are actually a couple different ways it can happen, and this is nothing you would ever be writing yourself. It just, if in an interview someone asks, what can you tell me about the garbage collector? What they're talking about is how the memory gets used and then reclaimed and used again. So that piece of memory was called the piece of garbage memory because it's not really useful anymore in your program. So there are basically 2 kinds of garbage collectors. One's called a mark and sweep or mark and trace garbage collector, and it's basically your main program would stop periodically, and then it would find all the variables that are like your global variables and find all the pieces of memory that they refer to, and then all the pieces of memory that they in turn also refer to, and so basically kind of go through the whole program and mark which one of these things are reachable, and then all the other pieces of allocated memory that were never reachable by any global variable are then garbage, and they can be deleted and marked as free and able to be used for future memory allocations. There's also a technique called reference counting. So say for example I had an object in JavaScript where I might say like x equals some array, some JavaScript object, and then I also say y equals x. So in JavaScript, these things refer to the same thing. So they'd be allocated. There'd be some object allocated in memory here, and you'd have both x and y pointing at that same piece of memory. Just ignore this one. And if later on I say x equals 7, and remove the reference of x to that variable, well, y still is referring to it, so it can't yet be freed up. And so what a reference counting garbage collector does is it actually keeps a little count, has a little piece of memory associated with each block, and it might count like, I have one reference to this thing now, and every time I add another reference, it'll increase it, so now I have 2. And it just keeps that track of that running count. How many times is this memory referred to? Usually it's either 1 or 0, but sometimes it can be, like in this example, 2 or higher. But once you get rid of the last reference, and now there's 0 references to this piece of memory from any other part of the program, then it can be deleted. One of the problems of a reference counting system is when you have loops or cycles in your memory. So if I were to have a linked list, say I had a linked list of, and I'll talk about linked lists a little bit later, but I might have things like this, where I have a list and it has 2 elements in it, a 10 and a 20, and then these next pointers. And if I somehow make it so that this thing points back on itself, any reference counting thing would say there are 2 things referencing this, like maybe some global variable. There's one thing referencing this, but then if I get rid of this reference, I'm going to now have one thing referencing this, but it's a cycle. It's a loop where there's no way in. Like there's no variables where you would actually see this memory, and so the referencing counting, if it's not very sophisticated, could end up leaking memory. So this is what's called a memory leak, and it can happen when you have variables where you're still referring to memory that you're not using, or you kind of continuously add your use of memory without using them in your program, but you kind of keep collecting and collecting it, and over time, long-running programs that have memory leaks will actually take more and more and more memory until they crash the computer because you run out of memory. So things like this could cause that. Okay, so we've covered the basics of how memory management works in a computer. You have the RAM use, the heap, which is that area of RAM that is available for your program to dynamically allocate memory as needed. We talked about dynamic memory allocation. The thing opposite of dynamic memory allocation is called static memory allocation. Some programming languages allow you to just allocate a big block of memory, and it's always the same. But for the most part, we're always using dynamic memory allocation in some form. We talked about automatic garbage collection when there are different flavors of marking and sweeping or marking and tracing, and then reference counting would be another way. And we talked about the importance of memory leaks and how those can affect your program over time. So the next topic, now that we've kind of covered that, is the other kind of memory that programs use, and that is called the stack. So the stack in a programming language is the place where whenever I create a new function, basically, data is allocated for me in a way that can be automatically released when the function's over. So suppose I have a function, call it foo, and if I might have something here which has a variable in it. Maybe I have another variable that's like a string, etc. When I call this function, these variables have to get allocated somewhere. Now, it's possible they could be allocated on a heap, but oftentimes programming languages implement these things on a stack, and also importantly, they keep track of which function is calling which. So if I had another function called bar, which calls this function foo, then I could allocate the data for bar, and then whenever I call foo, the memory gets allocated for foo, and then when foo returns back to bar, I could get rid of all of this data. So one of the things that a lot of computer programs use is called a stack. Now I'm going to draw the stack. You could draw it in two different ways, but it's a block of memory, and let's do it like from the bottom up, just to kind of keep things simple. There's a thing called a stack frame, and if you think of this memory as like this is all the free space up here, and this is called a frame, or a stack frame for a function. So say if this was the function called bar, and if bar had some variables in it, that data could be stored inside of this stack frame instead of going out to the heap. And the heap would be another block of memory somewhere else that's dynamically allocating different sections of different sizes all over the place. But in a stack, memory gets allocated in a very systematic way, where the last thing you allocate is going to be the first thing you free up. So if I had another function called foo that bar calls foo, it's going to create another stack frame. So the function of foo and all its variables get stored in the stack frame. But the other thing that's important to notice is that there's a return address stored in the stack frame. So when I call the function foo, I have to know where do I continue executing once foo is over. And so I'm going to I want to free up all this memory and start the program back from where the function call for foo happened. So what happens is you end up with a stack where every time you do a function call, another stack frame gets added with the local variables that are used in your function allocated in the stack, and the return value of the function, or the return pointer to the code that called your function. And so as you call functions deeper and deeper in your program, the stack gets bigger and bigger and bigger, and then when a function returns, the stack shrinks back down again. So that is kind of another way of automatic memory allocation that can be a lot faster than using a heap and doesn't require a garbage collector, but you have a limited amount of space. So typically the stacks in things like the browser or in Node, you might be able to have maybe 10,000 functions nested inside of each other. You'd call a function 10,000 times or 10,000 different functions. And before you'd run out of memory, depending on how many variables like each of those functions have. So the stack is very efficient, very fast, but it's limited in its size. You almost never have to worry about this in most programs unless you are using recursion. So let's talk a little bit about recursion. A recursive program or a recursive function is one that refers to itself in order to solve a problem. And usually this is used when you have a kind of complex data structure or complex problem where you can solve smaller versions of the problem, and then you can combine those solutions to be the larger solutions. A very common example is the idea of a Fibonacci series. Fibonacci numbers is a commonly used function that's very simple to write that uses recursion. I'll just use it as an example. A Fibonacci series is a sequence of numbers that begins 1 and 1, and then the next number in the sequence is the sum of the last two numbers. So the sequence that goes 1, 1, 2, because 1 plus 1 is 2, then 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. It goes on like this forever. So you could ask, what is the 0th Fibonacci number, the 1st, the 2nd, the 3rd, the 4th, the 5th, the 6th Fibonacci number series? You might want to say, I want to write a function that computes that. So if I have a function, Fibonacci, and I'm going to say n would to return the nth Fibonacci series. Well, if n is either 0 or 1, the answer is just 1. And this is called the base case of the recursion. So you'd say if n is less than 2, we'll just return a 1. Okay, so we've handled that. But now, if for any other larger Fibonacci series, we can just go look at the definition of the Fibonacci sequence, which is it's equal to the sum of the previous two elements. So I can just say return the Fibonacci value of n minus 2 plus the Fibonacci value of n minus 1. And that's it. So this program will return any Fibonacci numbers. I could call that on Fibonacci of 10, and it would return the correct value. Now, unfortunately, this program is actually pretty slow, but that's going beyond the scope of what I'm talking about here. We're just trying to define recursion and how it is used on the stack. So this Fibonacci program is an example of a recursive program, and it will add elements to the stack every time it recursively calls itself. And so if I call Fibonacci on a number 10, then it will end up calling Fibonacci 10 times, as it goes in depth. The depth of the stack will be 10 elements in the stack before it returns back from that, and your stack gets cleared up again. So you can have recursive calls which end up being too deeply nested, and then you can run out of memory in the stack, and that usually crashes your program. There are two other topics I wanted to mention just when thinking about a computer program stack, and that is, we already talked about stack overflow, and when the stack gets too deeply nested and your program can crash, but it's the idea of call by reference or call by value. These terms could be asked you in an interview, and whether you understand what they mean. And it's sometimes also called, whether you're copying values or on the stack or not. So in JavaScript, there are two cases where references to parameters in a function are either copied or just the reference is passed in, and oftentimes you need to know which one of these it is. So suppose I have a function and it takes a number and a list. I'll just an array called A. Now JavaScript is a language where you don't really have control over whether it's calling a particular function by value or by reference. So numbers are passed by value, and arrays are usually passed by reference. So what that means is that the calling function has to be able to expect that function f, that the function might be able to modify any variable called in passing in call by reference. So how does this relate to like a stack? Like if I were to call, I'm calling my function f, and it allocates memory on the stack for something, and it's going to have an a, and I think I called it n here. So if n is a number, it's just going to put that number directly on the stack. So if in some other part of my program I'm calling my function, I'm calling my function foo of n comma a. If I pass a number in for n which and the function modifies the value of n inside the function, the outer function doesn't see that modification. So if I say something like n equals 7 here, and inside the function foo, if I just write function f of n a, if I say n equals 22 in the middle of this function, it's really only modifying this number on the stack. It's not modifying the original number. Here, n is still going to be equal to 7 because this number was copied onto the stack instead. So that's called call by value. So the value of that number was taken out of the variable and put on the stack, and so the inner function f is going to have a copy of the value, and it can modify it as much as it wants, and it's not going to change the value of the other function. Now, because arrays can be really big and JavaScript objects can be arbitrarily big, JavaScript didn't want to make all of those functions, those parameters to be called by value. So they don't copy the whole array whenever you call a function. They just pass a reference to it. So if in this same code here I had something that said like A has a particular value of 1, 2, 3, and if down in my function I said A dot push a 7, then that is actually going to modify the original array. So you'll end up with A being 1, 2, 3, 7 now. And that's because it's called by reference, which means that JavaScript doesn't make copies of arrays when it calls them on the parameter. So this array here is itself a pointer to a block of memory on the heap somewhere that has the elements of the array. So when you pass in a variable, an array parameter, it doesn't take up very much space on the stack. It only has to have the address of memory where that array actually lives in memory on the heap, as opposed to copying the whole array into the stack or copying a separate copy of the array on the heap. So it is good to know which types of things, and in JavaScript it's basically in most programming languages the things that are like strings might be copied, called by value. Things that are numbers are called by value, and things that are like more complicated data structures like objects, dictionaries, lists, arrays, those things are usually called by reference. All right, the last topic in having to do with the stack is just talking about exception handling and a little bit of knowledge of like what is exception handling doing, and what is exception handling first of all, and how does it relate to the stack. And again, you might get asked this question in an interview, and it's good just to know kind of what's going underneath the covers. So when I talk about exception handling, I'm talking about a feature of a language that's usually called try, and another feature called catch. And then there's catch, and then there is usually there's a function called throw, where at some point in your program you're going to throw an error. And so what is happening here? So normally the stack, when you're calling functions and they're returning values, you're just adding you call a function f, you call another function g, you call another function h. It keeps adding on to the stack, and the stack is growing. And if at some point you have an error that is an exception, or that is going to basically mean that like you want to just throw away all the work that you've done for a lot, like there's no point in executing a bunch of code because there's been some exceptional error that's happened that wants you to unwind all the work that you've done. So what you can do there is when you call your function, you can put it inside of a try block, and then that means that you are ready for that function to have an exception. And then when it does throw an error way down deep, arbitrarily deep in this stack, you can catch that error here and then process, whatever error handling code you want to do for that. And in the process, it's going to delete all of the stack frames that for however far deep into the function calling tree you have, like it'll delete all of those functions in one go. Like those things, none of those functions actually return normally to their callers, and you're deleting all of the stack frames that were added to the stack in the course of running the program until it hits the throw, where you created some sort of error that it could have been something like a divide by zero. There's some built-in exceptions in our programming languages, like a divide by zero or running out of memory or things like that. Or there are other errors that are more generated by your program. You can decide to throw errors in the middle of your program. So anyway, the point here is not necessarily to cover try catch in detail, but just to know that when it comes to the stack, what's happening is it's throwing away all these stack frames at once when you throw an exception, and it just continues on the program inside the nearest catch block that goes along with the try block that was protecting that code. Okay, let's talk a little bit about asynchronous programming. So what is asynchronous programming? In most of the programming that we do, we know exactly what order everything is executed in theory. So I execute my program, line by line by line. If there are if statements, I either maybe skip some statements if the condition is false, or I include those statements if the condition is true. But essentially, I could go through and trace through each line of my program and know exactly when it is being executed and in what order. But on the web and web applications and things like that, we often have programs that have to interact with the outside world, and we don't necessarily know when things are going to happen, and we don't want to wait around for them to happen. We don't want to stop our program just waiting for something to happen. So we have what's called an asynchronous programming model, which is common in JavaScript especially, but is also available in other programming languages. So usually what happens is you have something called an event loop. So somewhere in the runtime of the programming language, there is a loop hidden from you that is looking at events that are happening and deciding to call back sometimes called callback functions, or just plain functions that call functions in your code when those events happen. And you've seen this if you've written on event, like a click handler for an interface in a web page, or especially if you do things like networking requests using the fetch API, where you'll call fetch to get some data, and then you want to process that data only after it returns back to you. So in the traditional way of doing asynchronous programming, you would pass a function off to something like fetch, where you're telling it call my function when this is done, and then you can go on your way and do other things that your program needs to do. But that has ended up causing a lot of complexity in code that it makes it very hard to follow, because you end up with a lot of nested asynchronous tasks happening, and it gets very difficult to follow. So if you're not yet familiar with it, you should be learning more about things like promises in JavaScript. And a promise is a special kind of data structure where you've encapsulated the value of something after it has been fully evaluated. So if you're fetching on a fetch data, you can put the result of that fetch into a promise, and that object you can pass around as a parameter to other objects. But if you want to process that data, you can call a function called the then function that will process the things after it has a real value that's been returned back from the server or whatever. And then you can nest these promises so that some promises can depend on other promises and things like that. So again, that's not kind of outside the scope of my talk here today, but just know that I think asynchronous programming, whether it's event-based and callback-based or based on promises, is something that you should be aware of, and I think you probably, in a lot of interviews, you will get some questions about it. Now, if you program through things like, like I said, like callbacks in the HTML DOM, for click handlers and things like that, you're already doing event problem, or there's the timer-based events and things like that. Those are all examples of event handlers. Of course, the frameworks like React also have different event handlers that you'll be writing as well. So that's something to be familiar with. Okay, moving on to the next topic. Performance concerns. I wanted to just really take a step back about all the things that might affect performance of a program, and as a developer, whether you're consciously thinking of these things or not, these are the things that will end up being the main drivers of whether your code works well or doesn't work well, and is fast enough. And so the most obvious one is the CPU time. Like if you're doing a lot of complex calculations on millions and millions of values, you're going to use up the CPU of your computer. And so that's an easy one, an obvious one to know about, that affects performance. But the other thing is memory usage. So every program not only has a limited amount of memory that it can use, but often when we see performance degrade on a computer system, it's not because there was a lot of calculations going on, it's because you were running out of memory. And in computer systems, there is an operating system concept called paging, and you have virtual memory. So say I have 4 gigabytes of memory on my computer, but the operating system says, well, I have got 30 gigabytes free on the hard disk, so if I run out of memory, instead of crashing some program to get it to release its memory, I'm just going to write some of that memory to the hard drive and into a file called a swap file. And in doing so, I'll make sure that all the programs continue to run, except the next time someone needs the memory or the data that used to be in memory and is now only on the hard disk, I'll have to read that memory from the hard disk and bring it back into memory so it can continue to run. So that is a huge driver of performance in, like if you have an old PC and you're running lots of programs and you notice everything's getting slow, what's happening is you're probably running out of virtual memory or you're running out of real memory, and your computer is now using virtual memory in order to keep your programs running. So just to be aware that is, and that can happen in the browser. You can use a lot of memory in the browser. It can happen on your server-side programs and things like that. So it's something to be aware of and to know how much memory your program is using. So obviously anytime where you have to access a hard drive, it's actually millions of times slower than accessing the memory in the computer. So accessing files is one of the slower things that computers do. So because hard drives are slow, even SSD drives are pretty slow compared to main memory. So that's something to be aware of that. And of course, any kind of you're doing communication with other computers, it takes time for the network request. It might take some latency just to transmit a request to another server and they get the results back, and you're depending on the speed of that external computer. So that's also something. So when people optimize, their programs for performance, it's these categories of things that they're thinking about optimizing. Okay, now that we've gotten through some of the preliminaries, I think it's time to talk about algorithms, and we'll also talk about data structures. So, algorithms are really just a fancy word for a sequence of operations that perform a particular task, and it's really no more complicated than that. But there are some kind of very popular algorithms that solve very common problems. And in a computer science course, you would learn how to implement these algorithms, and their characteristics. Now, one of the things that you will probably see is something which is called big O notation. And what people are trying to do is characterize how fast something is, or slow, or how much memory it might use or not, how little memory it might use. And the problem is, like, computers are getting faster and faster all the time, or you might run on a big computer or a small computer. How do you really compare, what's a good apples to apples comparison of two different algorithms when you have all these variables about how fast your computer is and so on? And so one of the ways is and in general these things are called complexity, or the order of the complexity of a program. It's kind of a weird word. It just means how much time does it take, or how much memory does it use. So let's talk about the time complexity of a program and how it relates to using big O notation, and how you can use that to describe different algorithms, compare different algorithms independent of the computer that they're on or the CPU that they're on. So imagine we have we're going to graph the time it takes to run a program versus the size of the input. So what do I mean by that? Like, suppose you have an array with 10 elements in it, another array with 100 elements in it. This is not to scale, but we're going to increase the size in one dimension. And then we could map out how long does it take that program to run. Like, suppose this might be 10 seconds, and maybe up here we measured how much time it takes to run that. Maybe that's 1,000 seconds. So, and if you can draw a line between those things, if on a graph that's to scale, that would be called a linear algorithm. So in other words, every time I double the size of my input, I'm going to double the time it takes my algorithm to do that. So examples of linear algorithms would be maybe looping through all the elements of an array one time and looking for a particular value. So those are linear programs, and they're generally pretty good algorithms that are just they have to read all the input in some cases and then process them. But there are other algorithms that are not as good, and you might have something called, and so let me just say that this algorithm here I'm going to describe as O of n, and that means that the function here that describes the behavior of that program looks like something that's linear in them. So if we're going to create an equation, I would have some sort of constant times the letter n. So for on a given computer and on a given CPU, if I were to plug in, I could create a constant variable which would be or I would create a constant which would convert from the size of the input program into the time in seconds to it. So and this function would fit on this line, and it would be approximately linear. So and you can compare that to other programs which might take, say, n squared time. So n squared, or O of n times n. So if the time is proportional to n times n, or maybe plus other things, like to get it really correct, it might have other terms in it, or even a constant term. But the main thing that's to note, like this is going to be the dominant factor. When n gets larger, n times n squared is going to be way bigger than n. So in general, this curve is going to look like something like this. And it's a square or quadratic, sometimes called a quadratic function. So, and that's going to dominate the behavior of your program. When you have an n squared program, you can only solve on any given computer. You can only solve programs practically up to a given size. Because at some point, this time might be days or weeks or months or whatever it is. Like you're not willing to spend that much time to solve a program, solve a problem. So, there are other programs which are proportional to the logarithm of a function. Now, just in case you're not familiar with logarithms, a very easy way to think of it is how many times can I cut a number in half before I get down to 1 or less. So, say for example, I have 1,000. How many times can I cut that number in half? So I go 500, 250, 125. What is it? 62 and a half. I'll just kind of round down. 31. Maybe 16, 8, 4, 2. Oh, 8, 4, 2, and finally 1. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, I counted that one extra, so there's 10 steps. So in 10 steps of cutting it in half, I got down to 1. And so you'd say like this is called the log base 2 because I'm cutting in half of n. So anyway, so it's basically, that gives you an idea of like what you mean by logarithms. So some programs are proportional to just the log of n. So as n increases, the program running time increases very slowly. Log of n looks like this, time, and this is log of n. So those are really fast algorithms. If they only depend on the log of the input size, then that's good. One example is called binary search, and I can show that real quickly why that would be log of n. Suppose you have an array of sorted numbers. So these are small numbers here, and these are the largest numbers here, and they all increase. If I were looking for a particular value, suppose I'm looking for a value, I'll just call it k here, that's sitting in the array. All the things here are less than k, and all the things on this side are greater than k. But I don't know where k is. I'm searching for it in the array. I don't have to I could write a loop that looks through every element until it finds k. That's going to be, in the worst case, k might be at the very end, and I would have to look at every single element in that whole array, and that would be a linear time algorithm. A faster way to look for something in a sorted array is to cut it in half multiple times. So here we have that cutting in half thing that I mentioned in the log n. So I might check to see this element first, right in the middle of the array. Is that equal to k? If it's larger than k, then I know that k is over on this side. If it's less than k, I know that k is over on that side. And so this would be the first step in the binary search. And other than that, I might say, well, let's look, so in this case it's smaller, so I'm going to look on the left side. I'm going to look in the middle of the left side. So of treating this now as the part of the array I'm interested in, I would look right in the middle here. And of course, in this case, I might have found it right away. But in general, I basically cut that array in half, cut the remaining part of what's left in half each time in a binary search. And so if I have 1,000 elements in this list, I only had to cut it in half 10 times to find where this value k is. So anyway, that's binary search and how it compares to linear search and why it's an O of log n algorithm as opposed to a O of n algorithm, which is a linear time algorithm. the other examples might be sorting. So if I have an array of numbers and they're not in any particular order, but I really want them to be in order, it's going to be 7, 3, 1, 0, minus 5, 2, 20, 40, etc. If I want these numbers to be in order, there are multiple ways of doing it. So and it's a really good exercise to actually write a few of these simple sorting algorithms yourself. So one is called selection sort, and it's kind of the obvious way you would think about it. If I were going to sort this array into order, I would say, well, what's the smallest element in the array? Smallest element in the array, I'm going to put it first. So your program would kind of check each of these, looking for the smallest element, and along the way it maybe found this one, the minus 5, and so you could either copy it into a new array or you could swap it out so that I can exchange these two elements. And so by doing that, I would end up putting the 7 here and the minus 5 over here. And then I say, okay, now I'm gonna find the next largest element. And again, you go through the whole list, and you'd find, say, that 0 is the smallest element. So then I'd have to exchange these two, and then put the 0 and the 3. So I'd exchange those two there, and then I move on to the next element in the list, which is this one here, and so on. So you can look at that and say, for every time I get one more element in the list, I'd have to have searched the entire rest of the list to find the next smallest element. So it's pretty easy to see then, for each of the n elements, I would have to have done work that's almost as big as the whole array, so another n elements. So that's why this algorithm, this selection sort, is an O of n squared algorithm, and it's not very fast, and you would not be able to do very, very large arrays on your computer. Where we would compare that to something like merge sort, and you can look up merge sort on Wikipedia, and you can see like a very small, it's actually not a very complicated algorithm. The idea behind merge sort is really based on kind of cutting things in half. So if I have this list or array of elements, and I'm going to merge it into another array, or I'm going to sort it into another array, what I would first do is I use that recursion again. So we would merge. We assume that the merge sort works for smaller arrays than the one we have, and then call merge sort on each of these two arrays, these small ones, and then once they are sorted, we can then copy the values from one to the other, where we keep track of what is the smallest element from each of these two lists, and we basically merge them together. So we always take the smaller of the two, say this one's smaller, I move that one into here, and then say, okay, now this is the next element in my list to look at, the next element up here, and then I compare it again, which of the two sides is smaller, and one by one kind of fill up this list. So it turns out if you analyze this, you can prove that this is an O of n log n algorithm to do merge sort. So sorting algorithms are ones where interviewers might ask you about different kinds of sorting algorithms. And there's the selection sort I showed you first. This one's merge sort. There's also an algorithm called quicksort, which you could look up, and it's actually an interesting algorithm if you're interested in algorithms. But it's one I think people are not writing very much day to day. I don't think any interviewer is going to expect you to know exactly how quicksort works. But briefly, how it works is very similar to kind of the merge sort, where you pick an element somewhat at random here, and you're going to rearrange the array such that all the elements less than x are on one side, all the elements greater than x are on the other side, and then you have x in the middle, and then you just call quicksort recursively on the two parts. And in general, this tends to be a n log n algorithm in the average case. So in the average time, this is an O of n log n. But it's possible that when you choose this element, this is called a pivot element, pivot, because you're kind of pivoting all the other elements based on that. Based on your choice of the pivot, you might end up getting unlucky, and the pivot is like always the smallest element of the array. Every time you choose it, it ends up being the smallest element. So you don't make a lot of work do a lot of work every time. So, but if you roughly cut the array in half most of the time, you end up with an n log n. Quicksort will work in n log n time. So in this algorithm, we say the worst case performance. So if you're really unlucky, it is just like the select sort. It's an O of n squared. But it turns out to be just in generally an average so fast that quicksort is probably one of the more popular sorting algorithms. And when you use a library that does a sort in JavaScript or in Python, those are generally going to be using quicksort to do this sorting algorithm. Okay, so that's kind of the basics of kind of an overview of algorithms, O of n notation, and when we talk about the time complexity in an algorithm, we're talking about how does it scale with this larger and larger size inputs? Is it log of n? Are you able to kind of cut the problem in half every time you reduce the problem down? It's linear if you have to read all of the data and you have to read it a fixed number of times, but at least go through it once. And if you have to go through every element multiple times for every and I compare it with every other element in the array, that's going to be like an n squared algorithm. So you should be familiar with kind of when you write code generally, is it linear, is it log n, or is it worse than linear? Does it have like a quadratic or other higher power algorithm? So those are things to think about and to know about, and just to be able to talk about that. And I think if you are ever talking about these different sorting algorithms, you should be aware that there are different ways of sorting things and that they have time complexity like these n squared, n log n, or n log n, depending on which algorithm you use. So, and I also mentioned earlier space complexity. So sometimes algorithms, generally it's not as big of an issue, or they don't talk about it as much, but if you allocate a lot of memory in the course of doing your program, it could have space complexity that's similar to time complexity. So how much memory do you have to allocate in order to implement your solution? And it could be more than linear or something, but generally space complexity isn't as big of an issue as the time complexity. So how long something takes to execute. Okay, and it's good to know like some basic data structures. So everyone in our course has been exposed to arrays or lists in Python. That is probably the most basic data structure that we have, and you should be very familiar with writing loops that look at every element in an array, or maybe choose random elements from an array or things like that. So you should I think binary search is a very good exercise for you to write a binary search on an array, and it will be expected that you would be able to do that in the context of an interview. Do it in real time in front of an interviewer who's someone looking over your shoulder. So you should definitely practice it and get familiar with that. But let's talk about a few other data structures that you might hear about or might talk about in the context of an interview. And some of those are the linked list, binary trees, hashing, and then maybe even B trees. Although I wouldn't expect anyone to be writing code for B trees in an interview, but you might be asked about them and want to know if you understand them. So let's talk about them in turn. So the linked list. What is a linked list? A linked list is a data structure where you are allocating a block of memory for every element of your list, and it has different kind of performance characteristics than an array. So if I had an array with the values 1, 2, 3, 4, etc., 5, 6. Okay, that's an array. And so in our dynamic programming languages, they often allow you to extend the size of an array without really thinking about it. Like if I needed to add something, I'd just do like a push command in here and I'd add another element of my array. But if you think about what's going on underneath the covers, remember we talked about the memory allocation, and we're going to have to find a block of heap space that will hold all the elements of your array. So underneath the covers, your programming language is dynamically allocating this array size, and at some point your array might grow big enough that it actually has to like allocate a new block of memory, copy the whole thing over to another place, reallocate that data structure, and it all's happening underneath the covers, but it does make your program slow down a little bit. So having dynamically allocated arrays can actually be kind of slow, and depending on what you need to do in your program, they might not be the best data structure. In general, these things are really fast. They're very highly optimized in our compilers, and the JavaScript runtime is optimizing it. So most of the time you will not ever notice performance effects from this. But interviewers might ask about them, and you should be aware of them. So there's another data structure called a linked list. In JavaScript, you might implement it as like an object. So you might have something like a value and a thing called a next pointer, which I will initialize to null here in this case. So this is called a node. We would just call a node in a linked list. And if I were to draw a picture of that, I might draw something like this, where it has two parts. It has a value part, and it has what's called a reference part, which would point to the next element of the linked list. So if there are no other elements in the linked list, usually this is drawn with like a line through it. So if I had a variable pointing to this thing, this is how I would draw it. But in the case of this like larger list up here, I would be adding elements to the linked list. So this next pointer would point to another node, which has another value in it, and that would point to another node, which has another value in it, like this, until the end of the list. So to construct something like this, you are actually creating new JavaScript objects for each node, and you're either using something like the new command, or you just or you can create objects with object literals, but they're creating new elements for each one, and you reference the next object from the previous object with the value of this next function, this next parameter here, or the next property. So let's get a little concrete. Why don't we write some code that actually uses a linked list? It's one thing to draw pictures and another to actually look at some code. So the typical functions you would have in a linked list would be insert an element at the head. So why don't we just write that function? We'll just call it insert at head, and then we're going to take a value, and it's going to insert it into a list. So a list here is going to be a reference to the first element of a linked list, and that's how we define a list, is its first element, and we call that each one a node. So we're just going to return a node, which is the value, has the value in it, and then the value of next is the whatever the previous value of the list is. So this is going to insert, it's going to create one new node and put it as the very beginning function of the list, and it's going to return the new node, which itself has a pointer to the previous list. So let's take an example. Why don't we write a kind of a helper function? We're going to say for each. We want to enumerate all the elements of a linked list and call a function on it. So let's see, I would do, so while the list is not equal null, we're going to call a function on the value of that element, and then we're going to advance the list to the next element of the list. So that should do that. So let's write a kind of a test function. Let's test our code a little bit, and let's let's create a new list. An empty list would be just pointing to null. You say that. And for I equals 0, I less than 10, I plus plus, let's just insert the numbers 0 through 9 into our list. So you're going to say insert at head at, the value I in the list. So notice that when you insert at the head, the value of the whole list changes because you're changing that list element. And let's see, does this work now? It's just had some syntax errors here. It does not work yet. I'm not doing anything with it yet. I haven't said. I want to call for each element in the list. I'm going to do console.log. So I'm just going to log out the value of each one of those. Okay, I just corrected a syntax error here. I had missing comma. And we can run that function, test1, and you see it's outputting all the numbers into the console, 9, 8, 7, 6, all the way back down to 1. So the reason it's in reverse order is because every time we are inserting an element, we're putting it at the beginning of the list, and all the remaining elements are going to get pushed back to the end. So insert at head, notice it's returning a object. So this is allocating something out of memory, a JavaScript object that has two properties, a value property, which is going to be where our value sits in that node, and then the next, which is a reference to the next node. So that is a basic list, and with an insert at the head, and notice that the order, if you want to say what is the complexity of this, inserting is constant time because it just has to create one node and return it, and there's no loops that you have to do to go through that. And iterating through all the elements of the list is order n, linear time. You have to go through each element of the list once. But now let's write something. Suppose we want our list to always be sorted. So we want to write something that's going to insert something into a sorted list, which is going to be a little bit more complicated, but still it might be something you might get asked in an interview. So let's call it insert sorted, and again it's going to take a value and the list in which we're going to sort this we're going to put this element into it. So how do we organize this? It maybe helps to draw a little picture. So hopefully you have some way to, even if drawing a diagram on paper, you could show it on your camera if you're doing a remote interview. So the idea in general is we're going to have the head of the list. This is usually a variable called head. It's going to point to a node with a value and the next. And that is going to point to another node with a value and a next, etc., until you come to a node with a null in it and then some value. So how do we, if we're given a new value and we want to insert that at the head, how do we do that? Well, first of all, we're going to create a new node for that. So part of it will be creating something with the new value in here. And now we have to find where in this list it's going to go. So the options are, it could go at the very beginning, somewhere in here. It could go between these two elements, or it could be between these two elements, or it could go at the end, but between those two elements. So let's just take a typical case where, say, it's going to go. We want to insert this element between these two elements. The steps are going to be, basically I have to kind of hook this into the previous. The new value will be in here, and then the next value is going to have to point to that, and then this next pointer will change because it's now going to point to that. And so we've inserted it in the middle. And the way we find out where it gets inserted is we have to go kind of look at each element in turn in a loop. We're going to say, we're going to find the first node that is greater than our element. So in that case, it would be this one. And we're going to have to remember like what the previous element was in the list, so that we can modify the previous node to point to our new node, and then the new node points to the old old next element. Okay, let's write some code. Maybe it'll be a little bit more clear seeing some code. Okay, so we know we're going to be having to keep track of a previous node, and we'll just call that, we'll start off as null, and a current node, which we're going to start off as the beginning element of the list. So now we want to go through this list, and as long as the current node is not null and the current node value is less than the value we're trying to insert, I'm sorry, let me wrap this around. Clear that. So as long as that node, we kind of keep searching through all the nodes until we find one that is greater than the value we're trying to insert. That's the point where we were trying to insert that new node. So once we do that, but to do that loop, we're going to basically moving both pointers along. I call them pointers, but they're like references to which node is the current one and which one is the previous one. So you could write previous equals current, and current equals current dot next. That would be a typical way you would write that statement. So to advance both of them together. You could also do something like in JavaScript, which is restructuring, using some of the fancier restructuring arguments. This is totally not necessary in the context of an interview, but they might ask you if you know about JavaScript being able to do this. It basically kind of does those two assignments at once. Then the next thing you want to do is like we know where it's going to go. We're just going to go between previous and next. So let's create a new node, and its value will be val, and its next we know is going to point to the current element in that list that we were looking at. And then there's a special case. So in some cases, we never had the current element we're going to insert in front of is the very first element of the list. In which case that the previous value of the previous node is null. So that's a special case. We say if the previous value is null, we're going to basically insert it at the beginning of the list. So in that case, we say, actually all we have to do is just return the node, because the node is already pointing at the node.next already points to the next element of the list, and we're all done. And so otherwise, what we're going to have to do is we're going to hook the new element into the previous element, and then we return the original list because that points to where the whole list now exists. All right, so now we need a new test function for our new function. Instead of inserted head, we're going to test insert sorted. Is that what I called it? Insert sorted, yeah. And it'll insert 0 through 9 again, and then print out the list in order. So test2. Oh, sorry, that I didn't rename it. Test2. Oh, I had a bug in my code here. This is insert sorted of list. And I'm returning list at the end. Let's see if that would work. There we go. So now notice it says 0 through 9, but in sorted order. So it inserted each of those elements in order because we searched for where it should go. Now the order statistics for that, or the O of n notation for inserting an element in a list, it depends on how big the element is. For small elements, they'll be at the beginning of the list and they'll be very fast. And for large elements, they'll go to the end of the list, and we've got to search all the way down to the end to insert them. So what we say is the average performance of this would be O of n. So because you're going through, on average, n over 2 elements. And the order statistics don't, that doesn't matter what the constant factor is, whether it's n over 2 or n over 3 or whatever. It's some constant of the value of the size of your input. So that's an O of n function for insert. But you end up with a sorted list, and you can then enumerate things that are sorted with that data structure. One other thing we can do in our test function, let's console.log out the whole list as it appears there. And you'll just kind of see, like, what does this data structure look like in a JavaScript debugger. And you see it doesn't look like the nice diagram of a block pointing to a block pointing to a block. It actually, the way the debugger prints this out is as a nested set of objects, where you have one object inside another object, etc., etc. But it is the same thing. It's just a different way of looking at it. And so here you see this is the first object, which is the value, and the next reference. But the next reference is pointing to another object. And so it prints it out in this kind of nested fashion. So you can see everything in the list in order, with the last one having next reference as null. But it doesn't look like a nice little boxes and arrows diagram, but that's just because the debugger doesn't know how to draw data structures like that. All right, on to the next data structure, a binary tree. So again, a binary tree is a very common data structure which has some nicer properties. Notice that if we are keeping things sorted, like in that linked list, it takes O of log n time to insert it. And let's talk about inserts in general for these 3 different data structures: arrays, linked lists, and binary trees, because they all have different properties. Okay, so we're going to insert, say we have a collection of numbers in increasing order, so they're sorted. And we have a collection. One collection is represented as an array. We'll just draw some pictures like this. Another collection is implemented as a linked list. Let's draw that like that. And the last data structure, and we have references to each of these things. And the last data structure is implemented as a binary tree. So this is going to look like this. We have a value, and then 2 things to the side here, a smaller and larger, like this, etc. So, and this is the reference to the root of the binary tree. So imagine what we have to do in the case of inserting an element into one of these data structures, how much work it takes to do that. Since all these elements are sorted, then the new element might go somewhere in the middle. Like suppose it has to go in between these two elements here. In order to put the new element here, we've got to shift everything over in the array. So you imagine like our array has extra space. And now I'm talking about what might be happening at the lowest level in the computer. I'm not talking about there's an API in your language for inserting an element into a list, but under the covers it's got to do this. So in knowing the performance, you have to know about that. So inserting an element into a list can be expensive, because if I insert something here, then I've got to copy every element forward one element first, and then I can put the new element in that position. So this is going to be order n for inserting an element into a sorted linked list as well. So, and that's ignoring the fact that you might have to reallocate the memory and the storage and stuff like that, but it's still order n to do that. In a linked list, it's also very similar. Similar to this, where it's O of n. You know, we just did this, where you have to insert it into a particular place, like say here, and so you've got to basically hook up that new element in the middle, and replace the previous pointer to that. So, but since we have to search for the position in the array that it exists, it's also O of n to insert that. But you don't have to copy a lot of memory around, so in some ways it might be a little bit faster. And now we have binary trees. So what do the binary tree data structure look like? A binary tree has a root element, which has some value here in the root, and then it has a left and a right child. So instead of a next value, it has a left and right, which point to other binary trees. So each binary tree is defined so that the value at any node in the tree is, this would be a sorted binary tree. The value of the root node would be greater than all the elements in the left binary tree, and less than all the elements in the right binary tree. That's assuming they're all unique. And you have, maybe it's greater than, equal, and less than, or something. But so you keep your binary tree sorted. If it's sorted and more or less balanced, depending on how the binary tree got built. If it's a balanced binary tree, that means the left side and the right side are roughly equal in size. And so we don't have like a long chain of things going off to the left or going off to the right at any point. And if you do the analysis on the algorithms of inserting an element into a balanced binary tree, you can see that every time we go to the left or right, we're roughly cutting in half the total number of elements we have to search for. And so when we compare, like, is the value greater than or less than the value at the root, I'm going to go to the left side if it's less, and on the right side if it's more. And we've cut off all the other half, so we reduce in half the number of elements we have to search for in the next pass. And at the child node, we'd look at the whether that value is greater than or less than its left and right nodes. And then we end up only having to do log n. Remember, every time if we cut something in half until it gets down to 1, that is the log base 2 of n number of times we have to do that. So that will mean that this algorithm for inserting in a binary tree is O of log n. And so and that's an average. Again, remember, this is average case, and that's assuming some things about the distribution of the tree and how it's set up. So you have roughly balanced tree. If it gets out of balance, then it can end up being just like a linked list, and O of n for that case. So I'm not going to write code for the binary tree insert and lookup, but just like I recommend maybe a binary search in an array is a good exercise, I would recommend trying to do a binary tree insert, binary tree lookup, and you can just write simple functions like I did, and maybe we'll turn this into a future video or coding example if you wanted to go through that and see how I would write it. So let's talk about hashing now. This is an area that I think a lot of people do not have a lot of experience in understanding, like what hashing is all about and how they relates to data structures and why those are good data structures or algorithms to know. And if you look at my table here, you can see insert has O of 1 complexity, and lookup has O of 1 complexity, as opposed to O of log n. So what does O of 1 mean? O of 1 means it's a constant time, means it doesn't depend on how big the hash table is, and it is just going to return its value very quickly, or you can insert something very quickly. It seems like kind of a magic data structure because it can do that. There are a few, depending on the implementation of the hash table, there are occasionally things that will cause it to be more than O of 1, but for the most part you can consider it to be a constant time data structure. Now the good news is that most languages that we were using, these higher level languages, have built-in data structures that automatically do hashing for you. In fact, just a plain old JavaScript object is kind of like a hash table. I'll show you what I mean. All right, just a plain old object. I'll call this a hash table. And we're just going to do this. If I say console.log, this hash table, it just says it's an object. And it's an empty object. And in JavaScript, you can add properties to objects just at will. And you give a key value and then a value to that object. And I can say, here's another key and another value. And now if I log out that whole object, the debugger will point out that it has two properties, key and key2. But this, even in JavaScript on your browser, this could have hundreds of thousands of properties, and it is actually an efficient data structure for storing these. And when you want to retrieve the value, you just use the key. You'd say, what is the value of the, if I use a particular key, and it will return here 1, 2, 3. And if you ask for a value that doesn't exist in the hash, you're going to get undefined. So you could test to see if something's in the hash table by testing whether it's equal to undefined or not. So JavaScript objects give you a perfectly good hash table, and so sometimes people call objects hashes, but they are, in Python they'd be called dictionaries, the things that have these properties. So they're a very efficient data structure. I can talk a little bit about, I think, under the covers, like how is this implemented, because we don't have, there are no magic computers, and they all have to fit into memory in some way, and they're ultimately, everything kind of looks like an array of bytes, because everything on a computer is a bunch of bytes together. So I'll just mention a little bit so you are aware of like how are hashes implemented, but you almost never have to implement one yourself. Okay, so the key to a hash table is what's called a hash function. So what is a hash function? A hash function is a function which takes some input and it scrambles it all up so you get kind of a random number out of it. And most hash functions, they're supposed to produce really good random numbers, meaning that no matter what values you give it, it's very unpredictable where, what the ultimate value will be, and yeah, it doesn't have, they don't clump up together. So if I call a hash function on the value 1, I might get some really big number or a string. Like sometimes hash functions return strings, but they're basically binary numbers or strings, something like that. And the hash function of a very similar number might create something that's totally different than that. So that's the property of a hash function. And so what do we do with that to create a hash table? Well, normally, one of the simpler ways that it's done is uses something called linear addressing and chaining. So I'm sorry, you can use techniques called linear addressing or chaining. I'm just gonna talk about chaining here. It's one of the simpler ways to do it. So imagine we want to allocate, we don't have very many values in our hash table yet, and say we allocate only like 100 elements. We're going to allocate an array. I'm drawing an array vertically at this point. Allocate 100 elements in this array, and they're all initially empty, so all null values in here to begin with. So say we take some value we want to put into our hash table, so we first compute the hash value of that value, and we get some big number out. And now we would need a number between 0 and 99. So we want to kind of clip off just some of the bits of this, and usually we would do something like a mod function. So we say there's an index which is equal to this number mod 100. So that returns a number between 0 and 99, uniformly distributed. So each random value of the hash function will go to another random location between 0 and 99. So say we get this value here, say 23 is this value for I, and then we would allocate some sort of node in here and put our value in there, and we basically use a linked list again. So if I have another value, suppose I have value 2, and it happens to, which creates a number 2, but it happens to be that the mod 100 of that value would equal the same value of I could still put it in this same slot of the hash table by making a linked list so that both values are represented in this element of the hash table. So that gives you an idea. You kind of have an array, which is a big index, and then you use your hash function to derive one of the indices of your array, and then every time you need to insert an element, you'd go through the linked list that starts at that index and see if the value's already in there, and if not, you'd add it to the linked list. And so you can see, even if I have like 100 elements in my array, suppose I would compare an algorithm that was doing stuff on just a single sorted linked list. Say a linked list would be 10,000 elements long. Well, on average, if I hash all those elements into a 100 index table, I'm going to have 1/100th the size of each of these individual lists will be 1/100th the size. So now they're on average only 100 long, and it might only take me O of 100, 100 operations to insert it. But typically what happens is you don't have many what are called hash collisions. You would size this array so that it's generally has only just a handful of elements, 1, 2, 3, 4, 5, or whatever elements in each index position, and if it gets bigger, if you put more elements in your hash table than that, they automatically resize the index table so that you have more elements to put them in, and you reduce the number of elements in each individual hash index position. But I think just knowing that is good to know how to do it. You probably are not going to be called on to actually write that code, but you never can tell. It's good to be able to know what's going on underneath the covers. Okay, so now there are only two more data structure concepts I wanted to address in this video. And one is having to do with databases and how databases are implemented. And the other is having to do with programming, the design of correct programs, and how some concerns that you might have about writing programs that are correct. So in the first case, is the B tree. So this is a data structure that, unlike a lot of the other data structures we're talking about today, exists kind of both in memory and also on the hard drive. So you think of, instead of allocating stuff in memory, like I talked about the heap before, we're allocating stuff in a RAM or memory-based heap. These things are written to disk drives and disk drive sectors and things like that. So a disk drive is typically consists of a bunch of what are called sectors, which are blocks of I don't even know what the average sector size is on a hard drive nowadays. Say it's 2 kilobytes or something like that. So but in a B tree, you kind of think of your data structure as having these blocks, and I think the B in the B tree stands for block tree. And it's very similar to having a sorted list of objects, except they're stored in blocks and in sequentially in blocks. So each block is like in a sorted array of values, but then it's like a B tree. It's like a binary tree. Remember, in a binary tree, we had a value, and then everything to the left was less than, and everything to the right was greater than. In a B tree, you have room for many, many more intermediate values. So you're going to store a lot of values per node of a B tree, or per block of a B tree. So you might have, say, 100 elements of your index fit within one block, and you would have, if it's less than one value, it goes to the left. Here, let me draw a picture. Okay, a B tree, I kind of think of it like kind of a node of a binary tree, except with a lot more values in it. And a block might not be completely full. Like maybe there's some space left over in a block. And I think of this also as being like written to disk. Like this exists on the disk, and you read it into memory to use it. But there would be values inside each of these. There's individual values, and these would be the kind of the key part. You have some sort of key where you're trying to search for a record in a database that by a given key value. And either the data exists, if the data is small enough, you can write it right into the index, and the data is right there. Or if there's more data than fits into one block, you can these could be pointers off to other blocks. And so then these blocks then have 100 keys each and stuff like that. So so to look up any particular value is quite similar to a binary search algorithm. You look at the top block, either the data is right there in the block, or you can tell based on the value of the key, where does it fit in sequence, which one of these, if it's, if the value you're looking for is greater than this, greater than this, greater than this, but it's like less than this, then maybe all of these things down here are things that are less than that value and greater than the previous value. So that's a little hand wavy, but that is the idea of a B tree, and it's good to know that the way that databases are implemented to make them fast is you have to have these. This would be part of an index, and an index is going to consist of, it's going to be implemented as a B tree or some type of B tree. There's a lot of variants in B trees and different structures like that. Different databases use different things. So that's a little bit about B trees, so you know them, and it's not the same as a binary tree. So that you just know the difference in what it's used for. Okay, now the last topic is a little bit random, but I think it comes up a little bit, and you might end up having someone in an interview ask you about this. And the idea is between mutable and immutable data structures. So what do I mean by that? Let me again draw a picture. So in most languages, you can have a variable, and I'm going to say that variable points to some sort of data structure, an object, or this could be a whole linked list or a tree or whatever. And you have some other variable somewhere else. It points to either a different data structure, or it might end up two variables pointing to the same data structure. And it turns out if you allow modification of this, so if at any time I have, maybe I have a 1 stored here now, and in the future I write my code so that, I erase that 1 and I put a 2 there now. Depending on the context, you may have solved a problem for referring to that via the A variable, but the C variable didn't really expect that value to change, and that you're going to end up with bugs in your code because you overwrote something that shouldn't be. So let me give you an example of how an immutable data structure would solve this problem. So suppose we take the example of a linked list. The way I described the insert operation before was as a mutable. Mutable meaning you can change it. Whenever I inserted an element into a linked list, it changed the list itself. At least the one that was the inserting it into a sorted linked list. So, but if you had some other part of your code that was referring to that list and didn't expect that list to be changed out from underneath it, you could end up with bugs. So what if you want to make sure that any previous reference you had to that linked list would never change, but I can still modify the linked list for for other parts of my code. So let's say there's a linked list, and there's our list, and this is maybe say some original pointer to it. Now suppose I want to insert an element in here without changing the original, but I want a new list which is identical to the old list but has a new element added to it. Well, one thing I could do is I could just copy the list, which is kind of slow and also obviously kind of wasteful because you're going to copy every element of this list. So I could copy the list and then use a mutable algorithm to modify the list, and that works. But there's also cleverer algorithms to this. So suppose the new element is supposed to go in between these two. So if you think about it, if I'm going to insert that, I could reuse all of the elements behind it. I just need to create copies of the ones that are in front of it. So my new one, I would make a copy of the first element and a copy of the second element, and those are linked together. And now this one goes to here, and this one then goes to here, and I get to share the last two elements here. I don't have to copy those and rewrite them. Each of these lists, if I start at the head, I can go down, I can enumerate all the elements of the list in order, and I can still enumerate all the elements of the original list in order, and they didn't interfere with each other. So this is what's called an immutable algorithm, and there exists a lot of algorithms, for all the different things we've been talking about. Binary trees, there's a thing called red-black trees, linked lists, etc., etc. There are immutable versions of them, and they come in handy when you have a lot of asynchronous programming and event-driven programming, where a lot of things are happening maybe concurrently or asynchronously to each other. You can use these immutable data structures as more. They're not as efficient as the mutable data structures, but they have this property that they don't change data out from underneath other pieces of code that you might not know about or might not know that you're modifying. So that is mutable and immutable. And that brings me to the end of my abbreviated video on algorithms and data structures. So obviously I'm not trying to teach a whole computer science course, but I think now if you go through all those questions and actually let's bring it up. We'll bring up all the questions in the survey and we'll see if you could now at least talk about each of these things. Okay, let's bring it back around to the original self-assessment survey we sent out. And I had listed this, and a lot of you said, I'm unfamiliar with all of these concepts. So I'm hopefully that now you at least can check the I can define it box, if not the practical experience box, which you could get by further practicing some of these algorithms, maybe writing some of them yourselves. But let's go through this list as a summary. Big O notation we described is a measure of what's called the complexity, but it's really just the running time of and possibly the space requirements of your program. And it's defined as a function of a power of the size of the data. So I have n elements in my data. You could have an O of 1 algorithm, which is constant time. You could have an O of log n algorithm, which is the log of the number, which is just like how many times can you cut it in half before you get to 1, or O of n, which is linear, meaning you read all the data, a constant number of times each, or it could be a slower algorithm like O of n squared, where you're looking at everything for every element in the array. You're also looking at every other element, and it gets worse. And if you actually have an algorithm which is called exponential, that means it's actually like 2 to the n or something like that. Those grow really, really fast, and you can barely do any problems on those exponential algorithms. Okay, memory management. We talked about the structure of RAM, how underneath the covers, the computer language you're using or the compiler you're using allows you to allocate memory from that RAM. And has a heap where you reuse that memory, and there are things like automatic garbage collection that free up the things you're not using reference counting or mark and sweep algorithms. We talked about recursion, and how the stack is used, and what happens when you make a function call in a program, and how part of the memory of your program is in the stack, and you're pushing new things on the stack every time you make a function call and then popping them off every time you return from a function, and how recursion allows you to call yourself recursively to solve a problem. Pointers. Pointers are a concept in the C and C++ programming language, and they're really what I would say are references to memory, basically. So a pointer is the address of the object you're talking to, and in JavaScript and Python, they're kind of hidden, but anytime you refer to an object or you refer to a data structure, underneath the cover there's a pointer. That variable holds a pointer to the thing. Call by reference and call by value we defined as different ways that function parameters are used, whether they're copied. Like small values tend to be called by value and copied to the underlying function. So if you modify that in the function, it doesn't change the caller's version of that variable. Whereas call by reference, you pass in a large data structure, that's not going to be copied for performance reasons. And then if you modify that data structure, the caller's version of that data structure is also modified. We talked about Stack Overflow and how the stack is limited, and if you have a very large amount of data on a recursive function, you might end up overflowing your stack and crashing the program. We talked about the linked list data structure and how we would insert and search in that. And we talked about the binary tree data structure and how that is used to search for things more efficiently with a log-n search time and log-n insert time. I didn't talk about sorting algorithms. So I think we'll save that for a future video. but I did talk about, maybe I did talk about sorting algorithms. I'm forgetting now. This is like the second day I'm recording this. But there are algorithms called, I think maybe I did, a selection sort, which is an n squared sorting algorithm. It's easy to write, but it's not very fast. There's something called merge sort, which is a n log n algorithm, because you recursively break it up in half every time and sort the halves. And there's something called quicksort, which is usually the preferred algorithm that most internal compilers use when using their sort libraries. And it tends to be, in the average case, very fast, like an n log n sort, but it can be, in the worst case, n squared if your data is kind of already nearly sorted, unfortunately. So we talked about hashing and how hash tables work, and the hashing functions take a number and return kind of a randomized number that can be very big, and then you can use the mod function to get kind of a much smaller range of a hash function, so for use in making a hash table. We talked about B trees for databases and how they're used and how they're structured. We did talk about exception handling and how the stack is unrolled all at once when you do a throw, or you throw an error and then it's caught by a try catch block. And we talked about memory leaks and how they can occur if you allocate memory and never free it, or if you build structures where the compiler doesn't know that it can garbage collect that memory. Whew. Okay, I think we did cover everything in that on this. I'll go ahead and edit the video together and see how long this is. But I hope you got something out of that. And I'll be taking questions on this, and we'll probably have some weekly work for people that want to continue to work on data structures and algorithms. But I think the best thing it will be to do coding questions. Pam is going to be running those every week, and so some of these, I think it'll give you coding practice, and it might even throw in some of these simpler algorithms as good exercises to code. Okay, everybody, thanks a lot for listening. If you made it this far, good, that's congratulations, and I hope you can answer. I can define it at least for everything in this survey the next time you take it.